In this lesson, we will explore how transformations affect the graph of exponential functions. With that, we want to bring back all the different transformations that we've already dealt with our other parent functions earlier in the course. So we know that a value represents whether a vertical stretch or compression or a reflection into the x-axis. The k value represents either a horizontal stretch or compression. D value represents a horizontal translation left or right, and the C value is a vertical translation up or down. So we're going to be applying all these transformations to the exponential function. So we want to recall the graph of any function of the form y equals a f at k x minus d plus c can be obtained from any base graph y equals f at x. Today we will be investigating transformations of exponential functions in the following form. Y is equal to a, which is in front of the base, b to the power of k x minus d plus c. And we know using mapping notation, we can sketch the transformed graph. As long as we identify what the a value is, the k value is, the d value, and c value. Just like the prior functions, those transformations, the k and d impact your x coordinate, the a and c represent and impact the y coordinate. Now with exponential functions, the parent functions, there's many of them because you have to base it on the base function. So that's the first thing you want to do before you start graphing any exponential function. Identify the base of your exponential function and then identify the a, k, d, and c. So for the following investigation, we will use the parent function and its properties. So in this case, the parent function graph is y equals 2 to the exponent of x. The base in this case is 2. The y-intercept is 0 because 2 to the exponent of 0 is 1. The horizontal asymptote is at y equals 0, which is your x-axis. The domain is x is an element of real, and the range is y is an element of real, but y cannot equal to 0. Because remember, we have that horizontal asymptote on the x-axis where y is equal to 0. Okay, in part A, we're going to investigate what happens when we have different a values. So looking at the equation given in A, we have y is equal to negative 2 to the exponent of x. So again, in this case, we identify the base of the exponential function is 2. So I would always just remind ourselves, it's just good practice to identify first, what is the base function? So the base function, y is equal to 2 to the power of x. Okay, so with that in mind, we know then that there's an a value of negative 1 out front. So using mapping notation, that means each coordinate in our parent function, okay, we're going to take each y value and multiply it by negative 1. So with that in mind, this is my base function, and this is y is equal to negative 2 to the power of x. Okay, so with all these coordinates, I'm just going to create my little table here. Okay, x values remain the same. However, the y value is impacted. Each y value is multiplied by negative 1. So that becomes negative 1 over 4. That becomes negative 1/2. This is 1 and negative 1. 2 becomes negative 2 and negative 4. And so quick little sketch. At negative 2, we're at negative 1/4. At negative 1, we're at negative 1/2. At 0, we're at negative 1. At 1, we're at negative 2. And at 2, we're at negative 4. Before drawing any of these functions, again, we want to make sure we identify the horizontal asymptote, in this case, at y equals 0. Okay, that's kind of our guideline because we know with the exponential function, it gets close to the asymptote, but it never crosses it. So then connecting. And this would be y is equal to 2 to the negative x. So what's happened is the graph y equals 2 to, so that base function is reflected into the x-axis. Okay, and as expected, because we know when a is negative, we're reflecting it into the x-axis. Into the x-axis, across the x-axis means the same thing. Okay, so again, starting with the same base function, what happens when a is 3? Now we know from previous functions a would be of 3 would, because it's greater than 1, would be a vertical stretch by a factor of 3. So that means, again, each of our parent function key points, we're going to take each of those y values and we're going to multiply it by 3. Okay, so this is my base function. I'm going to say y is equal to 3 to the power of x. Okay, so each of those y values, x values remain the same. So -2, -1, 0, 1, 2, negative 3 times 1 over 4, which would be 3 over 4. 3 times 1 half, which would be 3 over 2. 3 times 1 is 3. 3 times 2 is 6. And 3 times 4 is 12. Okay. So keeping in mind that a value of 3 means that we're multiplying all the y values of our parent function by 3. So graphing that, a -2, we're at 3/4. At -1, we're at 1.5. At 0, we're at 3. At 1, we're at 6. Keep in mind the scale. 2, we're at 12. And again, the horizontal asymptote is at y equals 0. Very, very important. That is a very critical characteristic of this function. There's a horizontal asymptote at y equals 0. So this would be y is equal to 3, 2 to the power of x. Okay, so because of that, when you're comparing it to the original function above, the graph increases at a faster rate. It's vertically stretched by a factor of 3. Okay, moving on. What happens when the a value is a number between 0 and 1? So something like 0.5. So again, always identify the base function. Okay, and from there, a is equal to 0.5. So that means each coordinate, y coordinate specifically, is going to be multiplied by 0.5. Okay, we know a value of a that's between 0 and 1 would result in a vertical compression by a factor of 0.5. So we're going to observe what the graph will look like. So again, here's our base function. Y is equal to 0.5 to the power of x. So with that in mind, again, the x values are not impacted. A only impacts your y coordinate. So this would become, x can remain the same. Okay, so 1/4 times 1/2, which would be 1/8. 1/2 times 1/2, which is 1/4. 1 times 1/2 is 1/2. 2 times 1/2 is 1. 4 times 1/2 is 2. Okay, so graphing that again, asymptote does horizontal asymptote is at y equals 0. So at -2, we're at 1/8, so very close to 0, but not quite there. 1/4. At 0, we're at 1/2. At 1, we're at 1. At 2, we're at 2. Again, so y is equal to 0. Don't forget to label your axes and the equation. So in this case, the graph is growing the graph increases at a slower rate. Okay, so to summarize, if that a value is greater than 1, we have a vertical stretch by a factor of a occurs. If, however, the value of a is greater than 0 but less than 1, that would be a vertical compression And we see then the graph increases at a slower rate. If, however, a is negative, so less than 0, then the function is reflected into the x-axis. Okay, so looking at B, now we want to see how K impacts our exponential function. Now, again, I'm just going to scroll back up. I just wanted to remind you that we're comparing again each of the different transformations based on what has changed from this original graph. Okay, y equals 2, because that's the base function. So again, whenever we're looking at exponential functions, we do want to always identify that base function, and those are the points that are going to be impacted when we're using our mapping notation. Okay, so looking here, we have y is equal to 2 to the exponent 3x. So we know the base. Again, I always want to just good habit. I mean, in this case, we know it's always 2 to the power of x, but let's get those good habits in there and identifying it first. Then from there, we see that something is being multiplied by your x, so your k value is equal to 3. Now, using mapping notation, that means each coordinate, x coordinate, I should say, is being divided by 3. So x over 3, but the y values remain the same. Okay? So also, which I didn't identify, but the horizontal asymptote in this case, we did label it, is still y equals 0. I should probably indicate that. Let's go back and just add that. The horizontal asymptote in each case is always, that has not been impacted with that vertical. I'm just going to put that in there. I mean, we did identify it on the actual graph, but we're just going to include that because that's a really important property of the exponential function. So we want to make sure that's in there. Okay, so with that in mind, we know this is the parent function, y equals 2 to the base function. And y is equal to 2 to the power of 3x. How does that impact? So each of our x values are divided by 3. So that x would be negative 2 over 3. Y remains the same. Negative 1 over 3 because you're dividing negative 1 by 3. And of course, the y value remains the same. 0, 1, 1/3, and 2, and then 2/3 and 4. Okay, so keeping that in mind, graphing this, again, the horizontal asymptote does not change. So we have y is equal to 0. And we have at negative 2/3. So 2/3, we're at 1/4. At 1/3, we're about 1/2. Oops, 1/2. 1/2. At 0, we're at 1. At 1/3, we're at 2. And at 2/3, we're at 4. And that is y is equal to 2. Okay, so as you can tell, the graph increases at a faster rate. Therefore, the graph increases at a faster rate. Okay. Moving on to B, we now have a K value of 0.5. So again, identify the base. Okay, K is equal to 0.5. So therefore, again, K impacts directly. So we're going to say x divided by 0.5. Y, we can simplify that. So it becomes x, y, 2x. Because 1 divided by 0.5 is 2. It's easier and looks visually appealing when we don't have a fraction on a fraction. So y is equal to that horizontal also has not changed. So again, this is our base function. So in this case, each x coordinate from our parent function with that base function y equals 2 to the power of x, it gets multiplied by 2. So negative 2 times 2, which is negative 4, negative 2, 0, 1 times 2 is 2, 2 times 2 is 4. And of course, the y values do not get impacted. Okay, so graphing that we have, I always start with the horizontal asymptote because remember that's that guard line. We know the function gets closer but does not cross it. So in this case, we're at negative 4. we're at 1/4, and -2, oops, -2, we're at 1/2, at 0, we're at 1, at 2, we're at 2, and at 4, we're at 4. Okay, so with that in mind, we can say that the graph increases at a slower rate. Okay, now what happens when k is negative? So again, always start with the base. Our k value is equal to -1 each coordinate. So it's going to be -x and y. The horizontal asymptote is not impacted. Okay, so then again, seems a little tedious, but we want to ensure that you, at this point, grasp all the different transformations and applying them all to the exponential function. So we have y is equal to 2 to the power negative x. So that means all the x values are multiplied by -1. So -2 times 1, which is +2, +1, 0, -1, -2. And of course, the y values remain the same. Okay, so again, graphing that, we have at 2, we're at 1/4. At 1, we're at 1/2. At 0, we're at 1. -1, we're at 2. And -2, we're at 4. Oh, notice that. So now it's been reflected into, don't forget my horizontal asymptote, y equals 0. We have, oops, I forgot to label this, 2 to the -x. Y is equal to 2 to the 0.5x. Okay, the graph is definitely reflected into the x-axis. The graph is reflected into the y-axis this time. So when k is negative, that means it's reflected into the y-axis. Okay, so in summary, what can we say? If k is greater than 1, then we know we have a horizontal compression by a factor of 1 over k occurs. If, however, the value of k is between greater than 0 but less than 1, we know we have a horizontal stretch. And of course, if k is negative, then we know we're reflecting it into the y-axis. So reflected into the y-axis. Okay, moving on. We have what happens when we add a d value, whether it's positive d or negative d. Okay, so if we notice here, I think we have, let's put it in black. Remember, our standards is x minus d. Okay, so with that in mind, we want to again identify always the base. So y is equal to 2 to the power of x. Okay, that's always our base. We always want to identify that first. So in this case, we have a d value of 2. So that means each x value is going to be moved over to the right 2. So with that in mind, using mapping notation, it would be x plus 2, and the y coordinate remains the same. The horizontal asymptote, of course, is still y equals 0. So this is y is equal to 2 to the power of x. My x, there's my y is equal to 2, x minus 2. So all our x values, we're going to add 2. So -2 plus 2 is 0, -1 plus 2, which is 1, 0 plus 2 is 2, 1 plus 2 is 3, and 2 plus 2 is 4. So 1/4, 1/2, 1, 2, and 4. So graphing that, at 0, we're at 1/4. At 1, we're at 1/2. At 2, we're at 1. At 3, we're at 2. And at 4, we're at 4. Mm, Okay, and of course, don't forget that horizontal asymptote at y equals 0. Y is equal to 2 to the power of x minus 2. So the graph shifted to the right 2 units. So the graph y equals to 2 to the power of x shifted, each of those points shifted right 2 units. And likewise, when d is equal to -2, I'm sure you can predict that the graph y equals 2x is going to move to the left 2 units. So again, d impacts our x coordinates by subtracting each of them by 2. Y remains the same. Horizontal asymptote is not impacted. So this is y is equal to 2 to the power of x. Y is equal to 2 to the power of x plus 2. Okay, so -2 minus 2, which is -4, and -1 minus 2, which is -3, -2, -1, and 0. And of course, the y coordinates remain the same. So we have, again, always start with that horizontal asymptote at -4 at 1/4, and -3 we're at 1/2, and -2 we're at 1, at 1, -1 we're at 2, and at 0 we're at 4. And this is y is equal to 2 to the power of x plus 2. Okay, so in summary, if d is greater than 0, we have a horizontal translation of d units to the right. So if d is greater than 0, we have a horizontal translation, d units right. And of course, if it's less than 0, horizontal translation, d units left occurs. And then last but not least, we have y equals b to the power of x plus c. So we know c is that vertical translation up or down. So we want to identify that c value. And then, of course, that impacts our y coordinates from our parent function. Our base function in this case, again, always identify that first. Y is equal to 2 to the power of x. So we know c is equal to 1. So using our mapping rule, that means each of our y values, we're going to add 1 to them. So this is y is equal to the power of x. So -2, -1, 0, 1, 2. So if we took 1/4 plus 1, that would be 5/4, 1 and 1/4. 1, it would be 3/2. 1 plus 2, 2 plus 1 is 3, 4 plus 1 is 5. Okay, so again, always starting with that horizontal asymptote. So y equals 0, -2, 5 and 1/4. So 1 and 1/4 would be about here. Oops, I did draw the horizontal asymptote, but what we didn't realize, or what I didn't realize, I didn't draw it at the right spot. Because our c value, we're moving everything up, that means our horizontal asymptote is now shifted up as well. So this is y is equal to 1. So the horizontal asymptote, I jumped the gun there and drew it at the wrong spot. We've just moved that up by 1. So we have -2 we're at 5/4, at -1 we're about 1.5, at 0 we're at 2, at 1 we're at 3, and at 2 we're at 5. Okay, so the whole graph moved up, but that means so did the asymptote. So the graph, base graph to the power of x, is shifted or translated up 1 unit. And all the coordinates went up by, that's right, all the points went up by 1. Okay, so base again is y is equal to 2 to the power of x. We know c is equal to now -1, so that means our base function is gone, each y value is going down by 1. So we know that means the horizontal asymptote is also going to move down by 1. So that means we would have, again, the new horizontal asymptote -1. So again, y is equal to 2 to the power of x. And then, of course, our coordinates, all our y coordinates from our base function y equals 2 to the power of x, all those y values will go down by 1. So again, the x's remain the same. -1, 0, 1, 2. To be 1/4 minus 1, which is net minus -3/4, -1/2, -1. Sorry, not -1. 1 minus 1 is not -1, it is 0. 2 minus 1 is 1. And then, of course, 4 minus 1 is 3. So -3/4, we're at -2, we're at -3/4, which is about here. Oops, right here. At -1, we're at -1/2. At 0, we're at 0. At 1, we're at 1. And at 2, we are at 3. There we have it. Okay, so y is equal to the power of x minus 1. So the graph y equals to the power of x is shifted or vertically translated down 1 unit. Okay. Okay. So we learned that if c is greater than 0, that means we have a vertical translation, and this is proper mathematical language. Translation of c units upwards occurs. However, if it's less than 0, vertical translation still, but this time instead of going upward, we're going c units downwards. And of course, the equation of the horizontal asymptote we noticed depends on that vertical translation. And it's always going to be y equals whatever that c value is. Okay, so now bringing that all together, we're going to sketch the following exponential function. We're going to state the domain and range, the y-intercept and equation of the horizontal asymptote. So again, as with earlier, we always have to fully factor out the k value. Otherwise, our transformations and our values of a, k, d, and c will not all be correct. So let's start with that. We know y is equal to 2 to the power of 2x minus 1. I'm going to put square brackets around here because I'm going to use my brown brackets. Plus 1. Okay, so it's very critical. As I said, you always have to identify what the base function is. So in this case, it looks like the base is 2 to the power of x. All right, so we're going to identify, see that? All right, so whatever the base is, that x is in its exponent. So in that case, it's 2. So we don't want to mix that up with the a value. It happens to be the same number, but we always want to identify what the base value is first. So then we're going to identify a is equal to 2. K is equal to 2, D is equal to 1, and C is equal to 1. So just to have our mapping rule nicely laid out, we know each mapping notation would be x over k plus d, a, y plus c. And we also learned the horizontal asymptote is always y equals your c. Okay, so keep that in mind. Okay, so because we know that our parent function, we've just used it through the investigation, we know that the values for x, we use usually -1/2, which is 1/4, -1, which is 1/2, 0 is 1, 1 is 2, and 2 is 4. So just remember, you're just substituting those x values into the function y equals 2 to the power exponent of x, and that's how we get the corresponding y values. So using our mapping notation, we know it's going to be x over k, which is 2 plus our d. And then we're going to say a times your y, so 2 times y plus your c, which is 1. With that in mind, then we know that the horizontal asymptote is, we can say horizontal asymptote is always y equals c. Well, c is 1, so y is equal to positive 1. Okay, so we take -2 divided by 2, which is -1 plus 1, which is 0. 2 times 1/4 plus 1, which is 3/2. Substituting x being -1, -1/2 plus 1, which is simply 1/2. Substituting y for 1/2, 2 times 1/2, which is 1, plus 1, which would be 2. Substituting 0, that's easy, that's 1. 2 times 1 is 2, plus 1, which is 3. 1/2 plus 1, which is 1 and 1/2. Or I'm going to actually express it as 3/2. And then 2 times 4 plus 1 is 5. 2 divided by 2 is 1 plus 1, which is 2. And then 4 to 8 plus 1, which is 9. Okay, so again, we have to have a scale that works, but let's see. We'll start with the horizontal asymptote. Again, that is our most critical point. We know that the function will get closer and closer to it, but will never cross it. So y is equal to 1 is my horizontal asymptote. At 0, we're at 3/2, which is 1.5. At 0.5, we're at 1.5. Sorry, 0.5, we're at 2. At 1, we're at 3. At 1.5, we're at 5. And at 2, we're at 9. And there you have it. This is y is equal to 2. And again, you can put the original or the factored form. They represent the same function. Okay, so making sure to answer all that's asked. We want to do sketch. We did that. State the domain and range, the y-intercept, and the equation of the horizontal asymptote. So the horizontal asymptote we did it already. So the domain. So remember, with the domain, x is an element of real numbers. There are no restrictions. However, the range, we know that y has to be greater than, in this case, the horizontal asymptote. So y has to be greater than 1. The y-intercept happens when x is equal to 0. And in this case, right off the graph, we don't have to sub it into the equation because we've already determined that. I'm just going to highlight it when x is 0, y is 3/2, and that's that point right there. So the y-intercept is, when x is 0, y is 3/2. Okay, so given the different transformations, we have for each transformation, state the parent function and then describe the transformation. So I can't stress enough how important it is to determine what the parent function first is. So in this case, our parent function is going to be y is equal to 4 to the power of x. Okay, so then from there, we identify the a, k, d, and c. So in this case, we have a is equal to -3. So with that, that means we have a reflection. The negative is always reflected into the x-axis because it's negative. Then we have 3, so it's going to be a vertical stretch by a factor of 3. And you would never say -3. -3 net represents the reflection. Then we have no k value because there's nothing in front of the x. We do have a d value. D is equal to -1. So we have a horizontal translation left, you tell me the direction, 1 unit. And how many units? Okay, that's it. There's no C, so it's also nothing to describe. Okay, looking at B, we have y is equal to 2 times 1/2 to the exponent of 2x plus 3. So again, the base function, the parent function, again, always, always, always identify that first. Okay, so we know y is equal to 1/2 to the power of x. And then from there, we can identify what the transformations are. We have a is equal to 2, so we know it's a vertical stretch vertical stretch by a factor of 2. K is equal to 2. Remember, when you're describing, you have to know what the scale factor is. So right away, we're going to say scale factor is equal to 1 over K, which is 1/2. So that means we have a horizontal compression by a factor of 1/2. Okay. C value, there's no D value, sorry, I should say. And then the C value is 3. So we have a vertical translation. Again, the direction, the units. So we're going to say up 3 units. Excellent. And last but not least, again, always, 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 we need to know what the parent function is first. And then from there, we can identify what the different transformations are. So we know in this case, it's going to be y is equal to 2 to the power of x. Now there is an a value. A is equal to 1/2 because it's out front of the base. So that means that's a vertical compression by a factor of 1/2. Right? We do have a k value, which is -1. So that means a reflection this time into the y-axis. And we have c is equal to -2. So that's going to be a vertical translation. We're moving the whole graph down. And how many units? So down 2 units. And we have it.